Hello everyone, it's Miss Lloyd, and we are looking at exponential and logarithmic functions. In this section, we're going to focus mostly on exponential functions. This is one of my favorites. I don't know why, it just logs and like exponential things just go whoosh. You'll see here in a second. So our exponential functions are where we have a variable in our exponent. So here, instead of, we have some a, which is some constant number, so it could be 2, 7, 9, 843, it doesn't really matter. The x is what's in the exponent, and we're only plugging real numbers into that exponent. The thing is, though, we could plug negative numbers in, we could plug positive numbers in. Let's get a look and see what this might do. So over here off to the side, if we don't know how to graph something, or if we don't know what it's supposed to look like, we can always make a little t-chart like I'm going to here. Again, we can have negative exponents. That's fine. It just causes it to move into the denominator, so we're going to have some fractions. We can also plug in 0 and some positive numbers, so I'm going to have a little bit of everything. When I plug all this stuff in, I would end up with 1 over 2 squared, 1 over 4, 1 over 2. Anything to the 0 power, aside from 0, is 1. 2 to the first power would just be 2, and 2 to the second power would be 4. And then I'll plot those. And so if I were to continue over to the left, we would be getting very, very close to 0, but we would never actually get there because we would keep having 2 to some power in the denominator. So it would get closer and closer and closer and closer and closer to 0, wouldn't actually get there. And you know what? I could add 3 in there and give us 8. And I have even more of an exact curve. There we go. So this is our exponential function. It kind of reminds me of a roller coaster, the one where you like sit there and it goes 3, 2, 1, beep, and then you just like zoom off and then you just go straight up. Those are really awesome roller coasters. This is also could be very familiar because it's what the graph started to look like when COVID first hit. Actually, exponential functions are used all the time when it comes to trying to predict the way a virus spreads, or also the way population spreads if we want to do something a little bit more positive. Now let's check out what happens if we have 3 to the x power. And here is our exponential function for 3 to the power of x. So the higher that number is, the steeper it's going to go because you're going at a faster rate. So instead of multiplying everything by 2, we're multiplying everything by 3. So we're increasing at a higher rate than with the 2 to the x power. So for these, I'm going to sketch these first two are A and C, and then I'm going to save the others for my kiddos. So we've already done our 3 to the power of x. I'm just going to move that t-chart over here and plot it. So this is my 3 to the power of x, and then I want to see what this might look like if I have 3 to the negative x. So I'm still going to start off with my same round of x values to plug in and try out. If I plug in negative 2 to that x here, that means I'm multiplying it by negative 1, which means I'm basically doing 3 squared. Same if I plug in negative 1, I'd end up with 3 to the first power. And 0 isn't positive or negative, it's just 0, so it's still going to be 1. And then when I plug in a positive 1, it's going to make it negative 1. So I've got 1/3 and 1/9 whenever I do 3 to the negative square or 3 to the negative 2, it'll give me 1/9. And then I'll plot these. What I've basically done is I've made a reflection across my y-axis because my x was negative. Next, there's this one-to-one property. So this is basically saying if we can make our bases the same, then if the bases are the same, the exponents also have to be the same. So if my bases are equal, so the number that has the exponent, if that is equal, then the exponents themselves must be equal. So looking at this, I see that my smaller base is a 2 and my larger base is an 8. So I want to see if there's a way that I can change 8 into 2 to some power. And I do know that 8 is the same as 2 cubed. So instead of 8, I'm going to replace it with 2 cubed because I know that those are exactly the same. So because my bases are now the same, this 2 cubed is equal to 2 to the 2x minus 1, Because these bases are the same, their exponents must also be equal. I can just say, okay, the 2's no longer exist. I have 3 is equal to 2x minus 1, and then I have a regular linear problem to solve. So my x in this case would have been equal to 2, and then we're done. So again, I like to try to make the smaller base, whatever the smaller number is, I like to make the larger base into that smaller number. And if they're asking you to do the one-to-one property, then it should be possible. I'm not going to give my students something that's like completely impossible and like, oh, you can't actually do this. If it's the one-to-one property. Later on, we will see, okay, what if we can't get the bases to be the same? How can we work that? That'll be our next section. So stay tuned. So another example, this is a little bit different. So I don't like working with fractions. My students know this. It's one of my F words. So I'm going to change this 1/3 to 3 to the first power. Anytime I have a fraction and I would rather have a negative exponent than a fraction, I'm just going to change that to a negative exponent. Now that I can see, okay, I have a nice pretty base of 3, I'm going to see, or I know, I can change 27 into 3 to some power. So that's going to be 3 to the third power. And because I have an exponent to an exponent here, those are going to multiply. So I've got 3 to the positive x now. And if I have 3 to the x is equal to 3 to the third, then my x has to be equal to 3. Again, I'm going to save some of these others for my students. I'm just going to give you guys some brief examples to get the gist of what we're talking about. So our next bit is when we have translations. So if we have a plus or minus on the outside, so it's not actually a part of the exponent itself, it's going to cause our graph to shift up and down. If we have something adding or subtracting with the exponent inside the exponent as the exponent, it's going to shift things left and right. And because it's in with my exponent, it's always going to do the opposite. So if it's adding to C, it's going to be shifting to the left. If it's subtracting C, it's going to be shifting to the right. So something that we're getting used to around now. So if I had just my 2x, or 2 to the power of x, and say I wanted to add 2, then what I like to focus on is this dot right here. And I'm basically just shifting everything up 2 places. It's like I've added 2 to all of my y values. So I take this and everything would move up 1, 2 spaces. And then this would be my new curve. Where I was getting really, really close to 0 but not touching, I'm now getting really, really close to 2 and not touching. Or y is equal to 2. It'd be a similar situation if I was adding 2 to the x instead. Just instead of messing with my y values, I'm now messing with my x because it's inside of the exponent, then I'm shifting everything to the left. So I'm taking those that were originally down here and I'm shifting them over to 2. So 1, 2. And notice I'm still approaching my 0. That hasn't changed because I haven't moved up or down. I've just moved over to the left. So this next one, we're just describing the transformations. So we have a minus 2 in our exponent. Because it's in our exponent, it's going to be affecting our x. We're either going to be moving left or right. And remember, we're always doing the opposite whenever it's happening to our x value. So it's like we're adding 2. We're adding 2 to our x values. It means we're moving to the right 2 spaces. We then have this thing called the natural base of e. So our natural base of e, this is our natural exponential function. You find this very often when it comes to things in nature or things we deal with every day. So we have it in a continuously compounding interest formula. So if you're interested in money, you'll see this e pop up a few times. It's also something that we just find that occurs in nature. So typically when we're mapping viruses or the spread of a population or even the decline of a population, then we're going to see that E crop up in quite a few places. And so if you were to plug in E to the first power in your calculator, we would get this number right here. So we could graph this as well. If I have an E to the X power, I can plug in my same positives and negatives and see what this looks like. And this isn't something people just memorize. Most of the time we use our calculators. I mean, there are plenty of people who have it memorized. I find other things to do with my brain, like remembering how I best like my coffee. If I don't remember that, someone might end up dying. As you can see here, it still looks like an exponential function, just in a few different places than 2 or 3, because technically this is somewhere in between 2 or 3. So someone was looking at some data and they were like, huh, this doesn't quite work with 2 or 3, and they were able to map it best with E. And this is what we find happens most often. I did show my students at the very beginning of the pandemic um, the graph of how it was spreading in China at first, and we were able to line it up almost perfectly with e to the power of x. So then here, this is just a test that you are able to use your calculator. So in your calculator, and you can pause this if you want to, just to triple check, you can plug in e to the 0.3 power. Hopefully you understand how to do that in your calculator. I'm going to save these other two for my students just to make sure that they know how to work their own calculators. And so when we plug in e to the 0.3 power, I use these little squiggles because it is an approximation. It's not exact because we are rounding. 1.3499. And so again, I did talk about interest a little bit. And so we have compounding interest. So depending on your bank, this could seem decently familiar. If you put your savings, your money in a savings account, it can collect interest. Also, if you have debt, that collects interest. My student loans are collecting, or were collecting, quite a bit of interest before the pandemic. So here stands for our principal or start amount, so what we originally put into the account. R is the interest rate. You're not really going to find a lot of interest rates at 4%. Most of the time, they're a lot smaller than that if someone's giving you money. If you can find something that's larger than that, dude, put all of your money in there. Like, it'll be really nice. And then T is our time in years. Oh, also our interest rate needs to be a decimal. You can't plug it in, say we have 4%, you can't just have 4. It needs to be put in as 0.04. And then N is the number of times we're compounding per year. So quarterly means we're doing it 4 times. Monthly, there's 12 months in a year. And continuously is a little bit different. We actually use this formula P times E to the RT. And so if you're compounding continuously, that E is the natural E that we were talking about above. So if I originally invested £6,000, again, I'm in the UK, so I'm using pounds for my students, and because, I get paid in pounds, and we have an annual rate of 4%, and we have our money in there for 7 years. We want to figure out which of these types of loans, or sorry, not loans, which of these types of savings account would rather put our money in. And really doesn't make a lot of difference if we have quarterly versus monthly versus continuously, if everything's still at 4%. So here, although I'm going to be making that comparison with my students, my principal or start amount was at 6,000. And then we're multiplying it 1 plus my rate. Again, we're doing the decimal, so 0.04%. That's my interest rate. Over my N in this case is 4, since we're compounding quarterly. And this is going to be times 4 to the 4 times 7. So we're compounding for 7 years. So a lot of times you'll just put some money in a bank account and then just leave it. My grandmother did that for me for my graduation from high school. She had put some money in, and I just let it sit there for a while, and I ended up with quite a bit more than what she had originally put in. And then that was my graduation present. It was really nice. So now we're just going to start simplifying. Inside, I would end up with 101 over 100. My exponent would now be the 28th power. We've got to do our exponents before we multiply. This tends to be where my students kind of get tripped up. They start to multiply before the exponents, but order of operations says we have to do those exponents first. And then we can multiply. So my finished amount after 7 years in that account, and this is in pounds, not tacos, 7,927 pounds and 75 pence. We do want to be careful on where we're rounding to because this is money. We only have two numbers after that decimal. And that is all that I have for you lovely people today. If this was helpful, please like and subscribe. If you think it would be helpful for someone else, please feel free to send it on. Spread the love.